and welcome to ChemVid. Today we're going to be going over nuclear chemistry. Now there are 3 videos on Canvas that cover these notes. That's because there's 3 main points to nuclear chemistry. The first one we're going to talk about is the nuclear chemistry in stars, okay, that happens in nature. The second part is going into more detail about what nuclear chemistry is and how we do it in labs. And then the final piece, the final video, is going to talk about half-lives and how we can calculate half-lives. All right, let's get started. First thing is nuclear reactions happen in stars. That is where all of our elements are made, okay? Well, all of the 92 naturally occurring elements are made, all right? And as a review, before we get too much into that, I just wanted to go over protons, neutrons, and electrons and the atom. So as a student, you have probably seen something that looks like this. You've got rings, and you have electrons on those rings. All right. And then you have a nucleus made of protons and neutrons. Okay, so neutrons are in the nucleus, and they help to buffer the protons, which are also in the nucleus. We'll go over that a bit later. And then electrons are outside the nucleus in what we call an electron cloud. So in this electron cloud, these electrons are zooming around so fast they actually fill an entire space full of negative energy, which we will get to in 2 units, I think, 2 units. So hold on to your hats for that. All right, let's talk about relative size. So when it comes to protons and neutrons are about the same size. If a proton was 1 centimeter long, then a neutron would be 0.000008. It would be 1.00008 centimeters. So as you can tell, that's actually not that much of a difference. It's a tiny little bit of a difference, and we'll go into details about why that is later. Oh, and it looks like I accidentally added an extra 0. So let me go back and fix that. Just 3 zeros. There we go. All right. So not a very big difference. However, electrons are very different, okay? They are extremely, extremely small, okay? So I'm going to write this out. If a proton was 1 centimeter, an electron would be 0.000000001. Very, very, very tiny. All right, let's write that in scientific notation. 1 times 10 to the -9th. So not only are electrons really little, but they are really little even compared to their proton buddies, who are also really little. All right, and for this purpose, or because of this, electrons don't have a whole lot of mass, and so they are going to actually not even be included in the average atomic mass. So when you did that worksheet on calculating average atomic mass, the reason we don't include electrons in the mass number or in the amount of mass that an atom has is because they are so tiny. But yet they're the coolest part of the atom because they're the ones that do the reactions that you see every day. So that is an electron. They are very cool. All right, electric charges. Hopefully you guys remember this from 8th grade science, 9th grade science, something like that. But protons are positive. Neutrons are neutral, which we show using a neutral sign of 0. And electrons are negative. Okay? So protons positive, Neutrons, neutral. Electrons, negative. Electrons and negative don't really sound the same like the other two, but that's okay. They're the one that's left over, all right? And electrons being negative, oh, that's so important to what we will be learning about and how atoms bond and everything like that, okay? So that's a little bit of a review on the patterns of elements. This is what every atom is shaped after. Protons and neutrons in the nucleus and electrons on the outside. And so based on that pattern, we can form new and more interesting atoms. And so that's what we're going to do next. How are elements formed? All right, so in stars, the first thing, you need a star. And inside stars, something's happening, and that thing is called nuclear fusion. In a star, there is a ton of energy and pressure building in that star. And because of that, we can have fusion occur. So because of that pressure and because of that energy, a hydrogen can bump into a hydrogen and they actually become a helium atom, okay? So I'm going to draw over here what's actually happening. So hydrogen has one electron and one proton. Another hydrogen has one proton and one electron. And what happens is when they come together and they have enough heat and they have enough pressure, something called fusion happens. And they actually become one atom with 2 electrons and 2 protons. And we know that guy as helium. So when we're talking about nuclear fusion, we're talking about atoms coming together and actually becoming one new atom, okay? It's not like a chemical bond where they share electrons and they're just like hanging out together, like sodium chloride. No, no, no. It's where an atom and another atom come together to create a new atom, all right? So that is what nuclear fusion is. It's the combination of 2 atoms and then they come together. Now for the next part. Fusion allows atoms to come together to become new atoms, but a star can only provide so much energy, okay? So inside of a star, if you look at the periodic table, all the elements up until number 26, which is iron, in case you don't recognize Fe as iron, all of them, hydrogen through iron, which is 26, can be made in stars. A star has enough power to hold these guys together and to bring them together to create new ones. So for instance, I'm going to write over here, if I had a lithium atom and I fused it with a hydrogen atom, it would become a beryllium atom. Why is that? Lithium is number 3. It has 3 protons. Hydrogen has 1 proton, so when they come together, beryllium would have 4 protons. You see, the protons are what give an atom its identity, all right? So a beryllium atom will always have 4 protons. It can have different neutrons, it can have different electrons, but it will always have the same number of protons. And that's why fusion is so fun. You really look at the protons that come together and you can predict anything. One more, let's do sodium. Sodium is number 11. And let's fuse it with a beryllium atom, which is number 4. Go ahead and see if you can find out which one that is. What new element did I create? If your answer is phosphorus, you are correct. Because all you have to do is add the number of protons and get 15. Then you look on the periodic table and you find which element has 15 protons, and that is phosphorus. All right, but this can only happen up until iron. After iron, the elements start getting so big that they actually need a little more help. So what happens after that is what we call a supernova. Supernova is when the star literally gets so much pressure and energy that it explodes into all the vast parts of space, okay? And in that explosion, it gives you enough heat and pressure that all the rest of the 92 naturally occurring elements can be created, all right? So, to sum up, fusion is what allows us to create elements. Elements fuse together to create new ones. Then, once we get up to iron, we need some more heat and pressure, so we have a supernova where the star explodes, giving enough pressure to create the larger atoms. And there are 92 naturally occurring atoms in our universe. The rest of them are man-made. So now that we've made all of these guys, let's go back to the original one. The first atom that we have in the sun is hydrogen, which means everything else is made from hydrogen, including carbon. That stuff that's in your pencil, you're actually holding a piece of the star. It's so cool. Anyways, hydrogen, since hydrogen starts this all off, hydrogen is the most abundant element in the universe. So it's the one that's there most out of all of them, okay? And that's why he can create all the other ones. All right. So this leads us, a lot of the things that happen in the universe lead us to believe that we have a common origin. So a common origin means that all of our stuff that we have now, matter, people, all that stuff, started from one place and then spread out, okay? So for instance, there's evidences of this. All four of these are evidence. The universe is constantly expanding, okay? So as we look out into the universe, we can see that it is moving out and out and out, which means that our universe doesn't have a set area or a set volume. It just keeps moving out, which leads us to believe that we all had to start somewhere and then started moving out. So the universe is constantly expanding supports the idea that we have a common origin. We all came from the same place. Another evidence is that all elements are made the same way. Since all elements are made through fusion, that means that wherever we started off from, we all had to start from fusion, and then we had more fusion, and then we had more fusion, and we were able to make up the rest of the world from the elements created by fusion. So common origin, all of their elements, everything that we're made up of, would be separated or would be made through fusion of elements and stars, and then it would just keep separating out and going out and going out, and therefore we all came from the same place. Another one is that all elements have the same structure. So since all elements are made out of protons, neutrons, and electrons, that means that all of our matter, all of the stuff that we are made up of, all is made up the same way. And if we're all made up the same way, we probably had a common origin, or an origin that we all came from. And then finally, one of the final ones that we're going to talk about, all elements on Earth are the same as the elements in space. Okay? What that means is that when you look on Earth, you find elements. We have carbon, we have nitrogen, we have oxygen, we have all these different elements. But as we go and as we explored the universe, we were able to see that not only do we on Earth have those elements, but also those elements exist in space. And so the elements that we have here are the elements that we have in space, and we're all made up of the same elements. Okay, so that goes back to these two, because if we're all made of the same things and they're all made in the same way, then most likely we have a common origin. Right, so let's see how this applies to our solar system, okay? Our solar system, like many, many other solar systems, are made in the same way. So after a supernova happens and a star explodes, the masses start coming together, and gravity starts to pull in those masses. And so then we get our sun, which is just another name for a big star, so it creates another star. Sorry, that's kind of hard to see with the yellow, but there you go. And then the gravity of the sun will pull in other clumps of matter, which we call planets, okay? And so here we have Mercury and Venus and Earth and Mars, the asteroid belt, Jupiter, Saturn, Neptune, Uranus, and then Neptune, sorry. So how these guys get pulled in are based on what the elements are made up of. These first four right here, these are what we call the rock element, or the rock planets. They're made up of really dense rock material. These guys out here are known as the gas planets because they are mostly made up of the lighter gaseous material. So when elements have come off of the sun and are starting to form, the heavier elements stay close to the source of their gravity, whereas the lighter elements, they go farther away. Because as you know, a light object can travel faster and farther than a heavy object. That's how our solar system was created. That's how many solar systems are created. And it's all based off of the density of the elements and how they come together and the gravity that pulls them together and all of that fun stuff. All right? So after you finish up this video, go ahead and go to the next video where you're going to talk about radioactivity and nuclear reactions.